So the idea behind the squeeze theorem, and this is very important, because the conceptual stuff is what allows you to understand how to do it. If you don't understand the conceptual piece, then there's no procedure that'll make sense to you. All right? What you're looking for are two functions that surround the given function. All right? One on the high side, one on the low side. So any two functions. The idea is that they should sandwich the inner function or squeeze it in. Right? The idea behind that would be if I knew the limit of the function that's above the given function and the limit of the function that's below the given function, that should give me a sense of what the limit of the function itself is. Right? And in some cases, it actually tells us the limit. Right? And you'll see in an example or two here how that plays out. All right? But the big challenge here is determining that relationship. I need, when I'm looking at the 1 over x plus 1, so we're starting off with one that we know how to do with N behavior model, and we're going to do it using the squeeze theorem. I need two functions that I know surround this one. All right, and two convenient functions. That's the main idea. All right, so 1 over x plus 1. Well, let's start off, actually I'll write this on the big board. Let's start off with just some numerical comparisons. What is the relationship between these two numbers? No, the relationship, not properties or characteristics. 1/2 is greater, right? All right, so if I wanted to represent these with the expressions, I could write it as, this would be the same as 1 over 2 plus 2, greater than 1 over 2 plus 1, right? Because the 2 plus 1 and the 3 are the same thing, right? So the idea would end up being that the bigger the denominator in a fraction, assuming the numerators are the same, the bigger the denominator, the smaller the number. So I want to see if I can do something with that information here. So I want this expression to be surrounded by two other expressions, but I want to use this property here. So I know that this has to relate to, let's just use 1 over x. Is the 1 over x plus 1 bigger or smaller than a 1 over x? Smaller. All right, so we have that relationship just based off of that fractional idea. The left-hand side's a little trickier because you might say, well, let me just go in the other direction, 1 over x plus 2, for example. And you could potentially do something like that because all you need is something that you know will be consistently smaller, right? The other idea is probably a little bit more universal, and I recommend going this way because it takes a little bit, or actually a lot of the thinking out of it. So I have, again, 1 over x plus 1. And 1 over x. All right, there's my 1 over x plus 1, and there's my 1 over x. All right, so it's kind of hard to see, but if we just focus on this area, we can see that this one is definitely less than that. All right, we could even bring it in domain-wise. Instead of negative 10 to 10, we can go 0 to 10. You could even go lower if you want. To really emphasize, maybe like for y, like negative 2 to 2, really get in there. All right, so I could do something like this. I can go 1 unit in the other direction. I could do something like 1 over x plus 2. See what that looks like. All right, it does look like the middle function is trapped in between the top and the bottom one. The other thing I can do, and I leave it up to you, it's going to work either way, but another thing I can do would be just to take the negation of the upper bound. So negative 1 over x. Because all that's going to do is reflect the 1 over x over the x-axis. So it guarantees that whatever that original function is, it's going to be between these two expressions. So you can go either way. It's entirely up to you. I like doing it this way with the negative 1 over x because it transforms into kind of more of a memorization or a procedural approach where you just say, okay, I know what the upper bound is, just negate it, I have the lower bound, I don't have to do any more thinking. All right. Now, the purpose behind this would be to find the limit of the outer bounds. So the limit as x approaches infinity of negative 1 over x, limit as x approaches infinity of positive 1 over x. All right, so I'm just focusing on the outer bounds. The idea behind that is I'm imagining that I don't have any way of figuring out what the limit of 1 over x plus 1 is. So I'm not even looking at that now. If I look at the outer bounds, those should be things I should be able to figure out. So left bound would be negative 1 over infinity. Right bound, positive 1 over infinity. In each case is equal to what? 0. All right, so now I'm going to associate a limit here. All right, so what this is telling us is that the limit of this is between a limit of 0 and 0. Now this might seem to not make sense. How can you be less than 0 and greater than 0 at the same time? But we can actually make a small adjustment to this, and it only works for extreme values of x. So for large values of x, we can transition to less than or equal to symbols, all right? Because the idea is that as we get closer and closer to infinity, everything is going to actually get closer and closer to 0. So things that might be less can actually, if you could get to infinity, could actually be equal to 0. So now what we're saying is that this is between 0 and 0. So common sense at that point would tell us that the limit is equal to 0.
Wait, what do you mean by for large x?
For, like, if I were to plug in x equals 120,000 or something like that. It's approaching 0. If I were able to get out to infinity, then I would be able to get to those zeros and have equality. All right. So that's the first one. And again, that's really just to kind of gear you towards understanding the process. If I ask you to find the limit of this question, you'd never do this. You would just find the end behavior model, plug in the infinity, and call it a day.
Do you have to add the equal to symbols under it, or
No, you can assume it. Yeah. Now this one, number 2, looks very much like one of those rules. Except the rule says as x approaches 0, this equals 1. This is not x approaching 0. What you might want to do is take a look at the picture and see what's going on there. Trig ones, I think, are easier because there's always some understood relationships associated with the trig that will make your life easier. So that's what this function looks like. But again, we don't care what's happening at 0. We care what's happening for extreme values of x. All right, very large values of x. So what I want to do is identify 2 functions that I know the sine function is in between. Just the sine function. What do we say?
I thought that just equals 1.
1. Oh, no, the rule? No, that's if x is approaching 0. Sine x over x as x approaches 0 is equal to 1. All right. Now, the sine function itself, if you were to actually just draw a sine wave, that would be between negative 1 and 1. Same thing with cosine. So that's a relationship we know to be true. All right? Algebra 2 pre-calc that came up over and over again. Right? If you draw a sine wave, it maxes out at 1, mins out at -1. We can trap the entire sine wave between these two functions. So what we want to do is somehow build the middle of this expression into the given. All right, so in order to do that, I'm going to divide everything by x. All right, so the middle of this expression is exactly the way we want it to be. Now if I find the limit as x approaches infinity of each part of this. You can kind of do it shorthand. You don't have to show it all the way. You're just finding the limit as x approaches infinity of each piece. What's the limit as x approaches infinity of this? 0. What about the upper bound? 0 again. Okay, and so therefore, since we know it's between 0 and 0, the limit as x approaches infinity of the sine of x over x would then be equal to 0. And graphically, that seems to be bearing itself out. Because if you follow the curve, keep going to the right, it does look like it's approaching the x-axis. If you're not sure, you could expand. Let's go to the right to 20. Yeah, it looks like it's closing in on that x-axis, so it's pretty safe to assume that's going to.
Is it just a coincidence that it like follows the same rationale as like the end behavior model, that if the infinity were to be in the denominator, then it would be 0?
Oh, like for the previous one?
Yeah.
Yeah, it's coincidental, but it's a frequent coincidence.
Okay.
It happens very often. All right, number 3. I'll just get you set up on this one. And then I'll shift gears and do the Ken stuff with you. It only takes a couple minutes. So again, you want to build towards the given expression, but you want to work with something that you know to be true. So this says the sine of 1 over x. It's still a sine function. And sine functions still only exist between -1 and 1, unless there's some other amplitude. All right, so that's a known fact. And by the way, it may not be something that you know yourself, but your calculator knows. So worst case scenario, type it into your calculator and see what the highest value and the lowest values are. Yeah, it's pretty rough to look at, but it does look like it goes as high as 1 and as low as -1. So you can pull it off the calculator too. Right. Then at this point, and this is where I'm going to leave you for this problem anyway, I want the sine 1 over x to become x squared sine 1 over x. So what do I multiply everything by? X squared. Then I find the limit, and then we see what we got.
Good afternoon, John.